Hello students, this is Professor Chalai, and in this video we're going to look at combustion analysis. By the end of this video, you should be able to determine the empirical formulas from a combustion reaction. As always, you can follow along with our chapter worksheets. Now, combustion analysis you won't really get into based on your textbooks in chapter 4, but I'm presenting it to you here because it shares a lot of similar themes with what we've been learning in our previous videos, which is looking at empirical formulas and molecular formulas from experimental data. So before we can actually look at a combustion analysis, let's look at a combustion reaction. A combustion reaction is simply a reaction with excess oxygen to produce water, carbon dioxide, heat, and or other byproducts. And let's look at an example of such a reaction. In most cases, when we look at combustion reactions, we'll look at reactions that contain compounds that contain carbon, hydrogen, and just one other third element. Let's call it X. So maybe its formula is CaHbXc, reacting with excess oxygen gas, right? We're burning these in oxygen gas to form carbon dioxide. So all of the C, we said that there were a number of C's, so a number of carbon dioxide gas. However many hydrogen that we had, so let's use a different color. However many hydrogen, however many hydrogen we had will help us to form water, usually water vapor because we're burning this. And we'll also form heat, right, from combustion reactions. Combustion is just a fancy word for burning, plus other stuff, other byproducts. So to reiterate, all of our carbons will burn with oxygen to form carbon dioxide. That's why however many A moles of carbon you had will form A moles of carbon dioxide. The amount of hydrogen that we started with will help us to form water, so hydrogen reacting with oxygen to form water. But because water has 2 moles of hydrogen for every 1 mole of water, however many moles of hydrogen we start with, it will be that many divided by 2 moles of water that we end up with. Let's look at a real practical example. If you burn just regular carbon solid in oxygen, right, gas, you'll just form CO2 gas. You won't form water or other byproducts, so it'll just be CO2 gas and heat. As another example, let's look at maybe hydrogen gas burning with oxygen. You'll form just water vapor. Oops, water vapor, gas, there we go. And to balance this all out, there's 2 oxygens there, so we'll just have something like that. We'll look at balancing in our next chapter, so don't worry too much about that. But combustion reaction, just think of it as reacting anything with excess oxygen. You typically form carbon dioxide, water, heat, and other stuff. Now, to figure out the empirical formula from a combustion analysis takes a few steps. So if you can figure out however many moles of carbon dioxide you have, you know however many moles of carbon you started with, right? Similarly, if you figure out how many moles of water vapor you ended up with, you can figure out however many hydrogen you started with. And finally, whatever is left over is going to be the third element. So if you find the moles of carbon dioxide and water, you can use that to find the number of moles of carbon and hydrogen, and then you can use that to sort of figure out the formula. Let's look at an example. Hopefully that becomes clear. So here we have a combustion of a compound containing carbon, hydrogen, and it gives us carbon dioxide and water. So we have some carbon, let's call it X, with hydrogen Y, that's our compound, reacting with excess oxygen to form some X number of carbon dioxide plus some, let's say, Y over 2 number of water, plus heat and other stuff. Okay, so let's first figure out the moles of carbon dioxide and water. let's start with carbon dioxide. So blue for carbon dioxide. We ended up with 1.60 grams of CO2, but we need to figure out number of moles. So we just divide by the molar mass of carbon dioxide. So molar mass of carbon dioxide is 1 times 12.01 grams per mole for carbon, plus 2 times 16.00 grams per mole for oxygen, which gives us 44.01 grams per mole. You'll probably use this a lot, so it might be a number that you'd want to memorize or have written somewhere. But 44.01 grams per mole is the molar mass of carbon dioxide, so you divide by that, which gives us the number of moles of carbon dioxide of 0.0364 moles. Now, remember, from a combustion reaction, however many moles of carbon dioxide you have is the same number of moles of carbon. So that's the same thing as the number of moles of carbon. Okay, let's look at water now. For water, we ended up with 0.819 grams of water. We need to divide by the molar mass of water. So molar mass of H2O is 1 times oxygen plus 2 times the molar mass of hydrogen, grams per mole, and that comes out to 18.02 grams per mole. The molar mass of water, again, one you'll use often, so you might want to memorize. Okay, so we divide this by 18.02 grams per mole to end up with 0.0227, nope, sorry. We end up with 0.0454 moles of H2O. However, we realize that however many moles of H2O we have twice as many moles of hydrogen, because for every H2O there are 2 hydrogens. So if this is the number of moles of hydrogen, if you multiply that by 2 to get, in this case, 0.0909 moles of hydrogen. So there we have our moles of carbon or moles of hydrogen. From here on out, everything is very similar to what we do for empirical formulas, right? We have carbon, number of moles, 0.0364. We have hydrogen, 0.0909. And we divide by the smallest one. So we end up with, the smallest one is 0.0364, so that's C1, H 2.5. Okay, they're not all small whole numbers, so now we need to try to, so this is divide by smallest. Now we need to multiply by small whole numbers. Let's try multiplying by 2. So 1 times 2 for carbon is 2. 2.5 times 2 for hydrogen gives us 5. So they're all whole numbers now. So this is the empirical formula. So once we get here, the steps are pretty much the same. The only difference is how do we go about figuring out the moles. In our previous calculations, we figured out the moles by using the mass and the molar mass. However, in a combustion analysis, we're not given the mass of the carbon. What we're given is the mass of the carbon dioxide. So the molar mass that we divide by is not the molar mass of carbon, but rather the molar mass of carbon dioxide. It gives us the mole of carbon dioxide, which gives us the mole of carbon. Similarly, for the water, we divide by the molar mass of water, which gives us the moles of water. And in this case, we need to multiply by 2 to give us the moles of hydrogen that we started with. Once we have that, everything else is very similar. All right. Number 22, you can try working it out by yourself, but it's a little bit tricky. It has an oxygen as well. So it's carbon, hydrogen, and oxygen. And I have the steps over here, and try to see if you can figure it out by yourself. Otherwise, you can just unpause the video and I'll show you how to work it out. Okay, in number 22, we have 3 elements: carbon, hydrogen, and oxygen. So we need to figure out each of these. Let's call it A, B, and C, the formula for this compound. Now we know when these burn with excess oxygen, we produce a number of carbon dioxide plus B over 2, right? Half as many water, because water has 2 hydrogens in it, plus heat and stuff, which we're not going to look at. Okay, so let's go about trying to figure out our carbons and hydrogens to start with. So let's look at our CO2. We have 1.6004 grams of CO2. We divide by the molar mass. Again, this is where I said memorizing these molar mass of carbon dioxide would come into use, would be useful. So for the number of moles of carbon dioxide, we get 0.03635 moles, which is also the same as the mole of carbon. Let's look at water now. The mass of water from the question is 0.6551 grams divided by the molar mass of water, 18.02 grams per mole, which you can calculate what I've just memorized. Gives us 0.03635 moles of H2O, which you multiply this by 2, gives us 0.07270 moles of hydrogen. So we have our moles of hydrogen and we have our moles of carbon. But what about moles of oxygen? Because we can't figure out this formula without the oxygen. All right, well, let's look at the oxygen. Well, we don't know anything about what the oxygen goes to form in this equation. It just forms stuff. But in this question, it tells us what the total mass of the sample is. So if we figure out what the masses of carbon and hydrogen are, because we already know their number of moles, we can figure out their masses, then we know that everything else would be oxygen. So let's do that. So before we can go about figuring out the amount of oxygen, let's figure out the mass of carbon. Mass of carbon, we know the moles, 0.03636 moles, sorry. To get the mass, we just multiply by the molar mass of carbon, right? 12.01 grams per mole. Moles cancel out. And for the mass of carbon, we get 0.4367 grams. We can do the same thing for hydrogen. We can have 0.07270 moles of hydrogen. So mass of hydrogen, 0.07270 moles times the molar mass of hydrogen. I'm going to use 4 sig figs so that I don't reduce my significant figures in the answer. Multiply by 1.008 grams per mole gives us, for the mass of hydrogen, 0.07328 grams. So in our total sample, this amount is taken up by oxygen, this amount is taken up by hydrogen, which means the remainder should be, the remainder should be oxygen. So let's figure that out. So the mass of oxygen, would be equal to the total mass, right? 0.8009 grams minus the mass from the carbon, 0.4367 grams minus the mass from the hydrogen, which is 0.07328 grams. And so all of this gives us a mass of oxygen of 0.2909 grams. Now that we have the mass of oxygen, we can figure out the moles of oxygen using the mass, 0.2909 grams divided by the molar mass of oxygen, 16.00 grams per mole, which gives us a number of moles of oxygen of 0.01818 moles of oxygen. All right, so that last step, I'll go over it again. The first two parts were simple. We found the number of moles of carbon dioxide, which is the same as the number of moles of carbon, which we'll use later. The second step, again, found the number of moles of hydrogen, which we just needed to multiply by 2 to get the number of moles of water, sorry, multiply by 2 to get the number of moles of hydrogen. All that's good so far. For the third element, and in this case the third element's oxygen, but it doesn't matter, it could be chlorine or nitrogen or anything else. We first needed to figure out what the mass of carbon is, what the mass of hydrogen is, using the moles that we already calculated. Subtract those masses from the total to get the remainder, and the remainder will be the mass of the third element. In this case, the third element was oxygen. And once we have the mass, we know the molar mass of the element, oxygen, we can get the number of moles of oxygen. So from here, all of that gives us the moles of each of the three different elements in our compound. Moles of carbon, moles of hydrogen, moles of oxygen, which means we can write our pseudo formula. So let's do that. So carbon, the number of moles that we calculated was 0.03636. For hydrogen, the number of moles that we calculated was 0.0727. And the number of moles of oxygen that we ended up calculating was 0.01818. Next step is to divide. There we go. Divide by the smallest number, in this case the smallest number is 0.01818. So we end up with C2, right? 0.03636 divided by 0.01818 is C2. H comes out to be 3.99. Let's just round that up to 4, and O1. So this is our empirical formula. It took a long time to get there, but we got there eventually. To reiterate what we did: moles of carbon dioxide, moles of carbon, moles of water, moles of hydrogen. Find the masses, subtract them from the total to get mass of oxygen. Use that to find moles of oxygen, and then from there on out we do our regular stuff for figuring out empirical formulas. All right, with that, I want you to pause and answer the next question, number 23. It's very similar. It might look very complex, but it's another combustion analysis problem. Here we again have a compound with carbon, hydrogen, and oxygen. See if you can figure it out. Okay, similar situation. We have carbon, hydrogen, and oxygen, which means we'll form carbon dioxide, water, and other stuff when we perform a combustion analysis. We can use a carbon dioxide to figure out moles of carbon, so let's do that. Let's start with carbon dioxide. For carbon dioxide, we have 28.320 grams. So 28.320 grams divided by the molar mass of carbon dioxide, which is 44.01 grams per mole, which gives us moles of carbon of 0.6435 moles of carbon dioxide, which is the same as moles of carbon. Let's look at water. We have 9.019 grams divided by the molar mass of water, 18.02 grams per mole. That gives us a number of moles of water of 0.5005 moles of H2O. We multiply that by 2, and that will give us 1.001 moles of hydrogen. All right, we have 2 of the 3 elements. Let's figure out the third element. The third element is, in this case, oxygen. But before we do that, they give us a total mass right here. We need to figure out the masses of carbon and hydrogen before we could subtract from the total. So mass of carbon, we take the number of moles, 0.6435 moles, times the molar mass of carbon, 12.01 grams per mole, gives us the mass of carbon as 7.728 grams. Similarly, we could do the same with hydrogen. The mass of hydrogen is 1.001 moles times the molar mass of hydrogen is 1.008 grams per mole. I'm using 4 sig figs just because I don't want to reduce the number of sig figs. And this will give us 1.009 grams of hydrogen. So if we want to figure out the mass of oxygen, we take the total mass. Again, total mass here was 11.027. 11.027 minus the mass of oxygen, which is 7.728. 7.728 minus the mass of hydrogen, which is 1.009. All of these are grams. So the mass of oxygen comes out to be 2.290 grams. Okay, now we can figure out the moles of oxygen. We know the mass, 2.290 grams, divided by the molar mass, 16.00 grams per mole, which gives us the number of moles of oxygen as 0.1431 moles of oxygen. Now we have our moles of carbon, moles of hydrogen, moles of oxygen. We can go ahead and write our formula, or pseudo-formula. So carbon, number of moles is 0.6435. Hydrogen, number of moles is 1.001. And oxygen in this example, number of moles 0.1431. Not whole numbers, so let's divide by the smallest number. In this case, the smallest number is 0.1431. So that gives us C, 4.5 approximately, H, 6.995, let's call that 7, and O, 1. But they're not all whole numbers, so let's multiply by small whole numbers. Try 2 first. If that doesn't work, try 3. If that doesn't work, try 4. So 4.5 multiplied by 2 is 9, so C9. H, 7 times 2 is 14. O, 1 times 2 is 2. So here we have it, our empirical formula for this compound. It's a long way to get there, many steps, but we got there in the end eventually. Number of moles of carbon, number of moles of water, then hydrogen, mass of carbon, mass of hydrogen to find mass of oxygen, moles of oxygen, pseudo formula, divide, then multiply, and we get our answer. Many steps, but I've outlined these steps up here. And again, the only way to get these down is to do many practice problems. So try number 24 by yourself. It's another practice problem. Here we have carbon, hydrogen, and chlorine, and let me know what you get. And if you're not comfortable in your answer, we can go it over together. Also try numbers 25A and B. They're simpler, they're not combustion analysis. And also 26 by yourself. And let me know if you have any problems with them. Otherwise, I'll see you in the next video where we will go over molarity and concentration. I'll see you then.